Okay, it is 3 o'clock, so let's get started. Today, it's my pleasure to introduce Elizabeth Spicer as a speaker in the BUL seminar. BUL seminar stands for Boundary Layer Urban Meteorology and Land Surface Processes Seminars Series. And I think Elizabeth is going to address the U today a little bit. You might have heard some of her seminars before when she talked about her measurements with the EM27 down in Houston as part of the Tracer campaign. She did that for her master's work, which she finished last summer. Before she came to OU, she got a BS in chemical engineering with a minor in chemistry from Virginia Tech University. Again, she joined OU in 2021. Finished her master's last summer, and since then she has been working with me on trying to get a better sense of what the urban heat island in Houston actually looked like during Tracer. And she has been fighting with some data sets, but she's going to be presenting some of her initial results today. Take it away.
All righty. Thank you, Petra, for that introduction, and thank you all for being here today. Do very much appreciate seeing all the faces in the crowd and online. All right, so today, as Petra mentioned, I will be discussing the urban heat island. And this is a general term for a phenomena that essentially just means that temperatures are going to be higher whenever you have a more anthropogenically influenced or urban area as opposed to a more rural area. And you can think about this phenomena from a multitude of perspectives. You can think about this with subsurface temperatures, so literally below the ground. Think about them from a surface perspective, so land surface temperatures, as well as looking within the boundary layer or the urban canopy layer. And the differentiation between these is extremely important because temperatures are influenced differently depending on where specifically you are measuring them. So in this figure by the EPA, you can see that the blue lines represent air temperatures and surface temperatures, surface being solid and air temperatures being dashed at night for a variety of different locations near and inside a downtown area. And the orange curves are representing a temperature during the day. And generally, you have the highest temperatures in the downtown area, whether you're looking at the surface or the air of the entirety of this area. So always focused around the downtown. However, you can see that the surface temperatures versus the air temperatures, there is some deviation between those, more so during the day than at night. But all of this is really boiling down to differences of the impacts of the surface and near surface energy budget. But for the remainder of this talk, I'm going to be focusing on the boundary layer. Once again, harkens back to the whole BUL seminar series. So the energy balance that I alluded to, I'm going to simply be putting as this top equation. So essentially we have net radiation equaling the sum of our sensible heat flux, latent heat flux, and what I'm going to be discussing as the storage and anthropogenic heat fluxes. Sometimes in literature, you'll see that these two things are combined, but for the sake of the study, it made the most sense to separate them. And this net radiation is defined a little bit differently depending on whether it's during the day or night, as you probably recall from your radiation classes. But the terms that matter the most when we're thinking about the boundary layer urban heat island effect are actually these last two terms in our energy budget. So QG being our storage heat flux and QF being our anthropogenic heat flux. So essentially the way that these things work is that for our storage heat flux, we have a bunch of materials that are essentially acting like a battery. During the day, they charge, so they essentially gather heat from the atmosphere and they store it, and then at night they release it back into the atmosphere, increasing the near surface air temperatures. And this occurs for a couple of different reasons, more so within an urban environment than in a more rural environment. The first of these being that urban canyons trap radiation. And so if you're unfamiliar with the term urban canyon, it's essentially when you have a bunch of very tall buildings, so think skyscrapers. So in a city center, you don't have one giant building taking up everything. You have a bunch of buildings with differing heights and with gaps in between them. And those gaps in between can be considered urban canyons. So they're great at trapping pollution and also radiation. And the other main reason that urban areas are very good at having a high storage heat flux is because of the materials they're actually made of. So think of building materials, concrete, asphalt, things like that. These things can have higher heat capacities compared to more natural materials. And if you think about it, in a city, you have a higher surface area of the things that are around you in comparison to a more rural area. So you've got all these tall buildings, smaller buildings. You've got a lot more stuff going on, and all of that stuff can better absorb heat compared to just like trees and grass and things like that. So this term is obviously going to be very important for looking at our boundary layer urban heat island effect, but then the other term, of course, is the anthropogenic heat flux. And so this is everything from heat generated by traffic to building, heating, and air conditioning, all that sort of stuff. So all the stuff that people are doing to actively generate heat in the environment. So both of these things play a big role in determining the magnitude and the effects of the urban heat island. And we can observe these by looking at our near surface air temperatures. And I'm going to be doing this within the context of the Tracer campaign. So this was a field experiment that had an intensive operational period in the summer of 2022 down in Houston, Texas. And this was a campaign that was from the Department of Energy's Atmospheric Radiations Measurements Users Facility. And the core of this campaign was focused on looking at the aerosols present in this very urban and industrial environment, the convection that occurred during this IOP, and how the two interacted. However, in order to fully contextualize everything, there were many scientists that were interested in the greater goings-on of the boundary layer, hence why we're wanting to look into the urban heat island. And Houston is a great testing ground for the urban heat island, as well as the other objectives for Tracer. So if you're unfamiliar with the Houston area, it is the largest city in the United States, fourth largest city in the United States by population, and the 9th by area. So it is a sprawling city. And as you can see in the top figure, it has a quite developed city center with lots of different skyscrapers in it. But once you move outside of the city center, it doesn't just go away. Houston does not go away. There are a lot of very busy roads, dense residential areas, which if you can see my mouse, I have circled here on this Google Images or Google Maps image. And right next to the very dense residential areas, you have very dense industrial areas. And this stretches out really past even the city limits of Houston and into the greater Houston area, which is just typically colloquially referred to as Houston in general. So it's a very large area with lots going on. And if you're also unfamiliar with Houston, it is bordered by not only the Gulf of Mexico, but also multiple large bays. So we have not only our land air mass that we're dealing with, but also a more maritime air mass that we are dealing with. And so that can frequently generate different bay and sea breezes, as well as land breezes, of course, from our land air mass that can move throughout the area and impact what's going on within the boundary layer. So this was one of the big questions that we wanted to try to investigate with this project, is how exactly does this urban heat island from our big sprawling city interact with these mesoscale features. And though this other point isn't necessarily an emphasis of the project as defined by a tracer, it is important to note that looking into the urban heat island has impacts past meteorology. In fact, it can greatly impact people that are actually living in Houston because of things like heat stress. So for those actually in the area, if you are not well equipped, this can be something that is life-threatening. So the urban heat island is not something you want to play with. So getting into some of the literature review associated with this work, there are some studies, or there have been some studies done with the urban heat island effect within Houston. And before I talk about some of the findings, I did want to point out that a lot of this work, whether in Houston or otherwise, hinges on this simple equation. So this UHII is this urban heat island intensity, and it is simply defined as the temperature difference between your urban area and your background area. However you define those, that is very much up to the person doing the analysis to actually lay out. And as I will find, no spoilers, well, slight spoilers, but it makes a big difference. So previous studies have found that Houston, on average during the summer, sees a modest urban heat island intensity of around 2 degrees. However, it can get up to northwards of 10 degrees Celsius. So this can have a big impact on those within the city center, and it really makes me want to ask the question of how does this impact what's going on within the boundary layer itself. But the one thing that I noticed while going through these papers in Houston and otherwise is that there are very few studies that actually look at combined analysis with the urban heat island, as well as other things going on in the boundary layer. So remember, I talked about the sea and bay breezes that are very common in Houston. A lot of times people are looking at one or the other, not a combination of both. And so this becomes a big motivating factor for looking into this, is not only just focusing on the urban heat island, but how it is influencing and influenced by other things going on in the atmosphere. And so to take a look at this urban heat island, I am going to be looking at near surface air temperature observations in a couple of different networks. So the ASOS network, I bet you all are familiar with, and these sites are marked in blue. But also on this map, I have all the stations from the Texas Commission on Environmental Quality Network, or the TCEQ network. And the main differentiating factor between these two networks is that the ASOS temperature is measured at 2 meters above ground level, whereas the TCEQ is measured at 10 meters above ground level. So we can almost have a multi-layered approach to our understanding of the urban heat island. So before we get into some of the more interesting plots, I wanted to make sure that we could actually observe some diurnal trends as well as some seasonal trends at our sites, make sure that we have data that we can actually work with. So I'm going to be focusing on this site with the star right here. All right, so these are two figures to represent the same data set taken at that site that I just pointed out. So on the left, you can clearly see that we have a diurnal trend with the maximum air temperatures seen in the afternoon, but we also have an increase in temperatures at night seen in the early morning hours. And this trend, as you can see on the right, is very repeatable. So we see it from the beginning of the campaign to the end, and we can also see that it has some magnitude differences as we go from some of the cooler, more moist months and into the hotter months, and then of course back into the start of fall. So it's nice to see that we have data that have some repeatable trends. However, it doesn't really tell us much about the urban heat island. And so in order to get that information, we need to look at both a background and an urban site. And so for a preliminary look at this, I chose these two sites, so just west of the site we just looked at, to be our background sites. I did this because I had both a TCEQ station and an ASOS station. And then I pretended like these sites were co-located for our urban site, so we can look at, once again, our 2 and 10 meter observations together and see how they compare. So let's take a look at May 4th of 2022. So here I have my urban temperatures plotted in orange, and I have my background temperatures plotted in blue. So the darker colors represent closer to the ground observations, and the lighter colors represent that 10 meter observation. And then the black line, trend line, is showing the difference, once again, the defined urban heat island intensity. So on this particular day, we don't have a massive UHII. It was about 3 degrees Celsius at most. But there are some other features that are interesting to see. So first, I would like to point out that, while we have our around 3 degree spread between our 10 meter observations here, we have a little bit of a larger spread when we look at our 2 meter observations. And this was consistent throughout many of the days I was looking at. When you are closer to the ground at our rural site, we tend to have a little bit cooler temperatures at night, whereas during the day, they tend to agree a bit better. And this is the exact opposite for what we see at the urban site. So at the urban site at night, we have pretty good agreement, at least slightly better than some of the deviations that we're seeing with our background site. But then during the day, we actually have an increased temperature at our 2 meter observation as opposed to our 10 meter. And so these point to interesting things that are happening in the boundary layer and processes that we need to consider as we contextualize this work. So Other than that, we essentially see what we would expect, that we've got an urban heat island at night. During the day, we have very close temperatures, except for we have a little bit of an urban cool island, actually, which is a feature that we need to investigate further. But generally, better agreement during the day than the night. It's exactly what we would expect to see. So what if we look at a different day? Let's say 2 days later. This looks totally different. Why? So our trend, our 2 meter and 10 meter, are very similar. We see the same sort of things where we have a cooler temperature closer to the ground at a rural site at night, and then in the urban center, we have a higher temperature closer to the ground during the day. That stays pretty consistent, but yet we've got this consistent separation between our urban site and our background site as we move into the daytime hours. We also have this really interesting drop. Is this the urban cool island? What exactly is causing this? Are we viewing different air masses? And what else is modifying the energy budget? Because surely not all of this can be attributed to just an urban heat island. So to add a little bit of context to this, I'm going to add back in the trend line from the 5.4 data. We're going to assume that that's kind of our perfect case for the urban heat island just for this example. And you can see that there's very clearly a difference from what we would traditionally call the urban heat island intensity. So that change in temperature isn't telling us all that we need to know when we're trying to separate the urban influences from what else can actually be going on. So if you look at the radar loop for this day, this 5-6 day, you can see that there's actually convection. This temperature drop at the urban site is due to convection that fired and just stayed right over the city center of Houston. So that's why we have the temperature drop. But what exactly is going on before then? We don't really know why this separation exists just by looking at temperatures, and radar doesn't tell us much either. So what exactly is going on? How do we scientifically determine the urban heat island as more than just a change in temperatures? Because it's obviously more complicated than that. And the plot thickens. So remember the map that I showed you previously. I picked these 2 sites and I said, okay, let's do an urban comparison and assume that they're essentially co-located. But next to my TCEQ site, I've got a bunch of other TCEQ sites. So what would happen if I were to pick one of these as opposed to the one I did earlier? Well, we have even more variability. And so not only is it important for us to understand what is going on within the atmosphere for each of our individual cases when we're trying to figure out the urban influences, but we need to be very careful when we're picking our sites so that we don't have things that are unintentionally changing what we see. I mean, depending on what site that I pick here, I could have an urban heat island intensity during the day that is 6 degrees more than what I would see at another site. And all of these sites are in like a 5-kilometer radius of one another. So all of this analysis is hyper dependent on the choices that you make as an analyst. And so it becomes very difficult to truly understand what is going on within the urban heat island. So of course, this breeds more questions than it gives answers, but that's all right for an introduction to the project. So a few of the key takeaways that I took away from this is that we have an option to use 1 or 2 different measurement heights. And I'm curious to see how using one or the other, or a combination of both, or even more data is going to give us, how accurate of an analysis is that going to give us. I find myself also asking how we can account for changes in air temperature that are not due to that urban heat island. How exactly do we find that out? What data do we need to include? What parameters do we need to add on to our urban heat island intensity calculation? And then also, how can we define the urban heat island intensity when we have high interurban variability? Do we choose one site and just say, well, that's the site and I'm sticking to it? Do we use an average between the sites? How exactly are we going to contextualize this in the best way for the analysis? But the nice thing is that Houston provides us a fantastic testing ground for all of these different questions with its sprawling urban area as well as its multiple bodies of water. So hopefully with the entirety of this data set, we can get some answers out of this. They'll be useful not only in this region and for this campaign, but can also be used in other regions also near bodies of water that deal with some of the same issues that we see within Houston. And so the future work list is long here, and this is not even comprehensive, but the number one priority right now is to establish a framework for calculating urban heat island intensity. And then I want to do a series of case studies, not only looking at periods of strong urban heat island intensity, but also cases where we have bay and sea breezes that we know, and we know where they went at what time, and we can see if there was an influence on the bay or sea breezes to the urban heat island or vice versa. And I really want to do this from a more holistic perspective. And so like the image on the right, which uses a Kriging interpolation of different sites in Oklahoma City, it was published actually not too long ago, but like this study investigated a more spatial approach as opposed to a site-by-site basis for the changes in temperature and wind speed. As you can see here, I would like to incorporate something like that. I'm not entirely sure if Kriging is the best way to do this. Perhaps some sort of dispersion model relationship to everything, looking at trajectories of air parcels, or even getting into machine learning, a way to interpolate all of the sites that we have within Houston. I'm not entirely sure what the best approach is going to be with this, but at the end of the day, with all of the variability that we see at the sites, not just due to what's happening in the atmosphere, but then also where specifically in the city you're looking, seeing everything from a spatial perspective is going to be critical to truly understanding what is from the urban heat island and what is from something else. So I hope to experience, I hope to get through all of this analysis in the future and hopefully share some results with you all in the future. But for now, that's where I'm at, and I'd like to thank the following folks for their assistance on this project, and thank you all for attending. So.
Thank you, Elizabeth. Are there any questions?
I have two. For the calculation of your UHII, did you average the 2 and 10 meter for that one black line you had, or did you only use 2 or 10 meter?
Great question. Let me go back to that so we can actually see. So as you can see, there are a lot of the pentagons representing the TCEQ sites and not a lot of the stars representing the ASOS sites. So this was a common issue that I was having, where there were a couple of ASOS sites that had a ton of data and actually stuck to that around 5-minute resolution that the website claimed, but then there were a lot that did not. And so I was using simply just the TCEQ data in order to make those urban heat island intensity curves, because simply with so little data, it's really difficult to determine actually what that urban heat island intensity should look like over time, especially compared to that 10-meter data, which is very nice and evenly spaced at 5 minutes.
And my second one is, have you ever considered seeing if an air mass change based off aircraft soundings? Aircrafts taking off from Houston can generate vertical profiles, and I don't know how archivable they are.
Yeah, I've seen other folks use data sets like that. It is not something that I have immediately considered, but I don't think it's necessarily off the table. I mean, we're very much in the early stages of this, and the direction in which this analysis goes is very much up in the air. So up in the air with aircraft. Anyways, so we'll have to see. We'll have to see how it goes. But that's a good point. Thanks for bringing that up.
Yeah, I guess I would wonder how you would get information about the spatial variability using the aircraft data. You would almost need data for more than one airport, which is possible in Houston. They do have 2 airports, but then you have to take into account that the plane, it's not a copter son that goes up, so we wouldn't have 2 profiles. So I mean, there may be value in looking at the data. It will not be straightforward to integrate those data into the analysis.
Most certainly. And I guess to add on to that, the other nice thing is with Tracer, there were a lot of sondes that were launched. So definitely we can use that data, but if we want to add to our number of observations, that might be something to consider. We'll just have to see how it goes.
So you talked about, you can go to your conclusion. So you talked about, it must be. or maybe it's just my brain doing brain things.
Okay.
So you talked about how urban heat island is more than just a change in temperature, and you need to find ways to kind of define that. What are potential ways you could see influencing your urban heat island than just temperature? Like what can you elaborate more on that kind of takeaway?
Yeah, and to provide a little bit more context, so it's not necessarily that I think that there are other things influencing the urban heat island. I think that there's other things that are going to influence the basic calculation of urban heat island intensity, this delta T. And so this May 6th case is a great example. So convection, obviously, this dip in temperature that we see at the urban site, definitely not anything to do with what's happening with the urban heat island. So that is immediately something that we can screen for using radar or other observations. And then the other thing is the difference between the temperatures at the background site. As you can see, it's a little bit more consistent. I say consistent. The 2 meter temperature is lower more often than we were seeing previously with the May 4th data. And I believe that this was due to the fact that there was actually rain the previous evening. And so this, I think, this is my working theory, could have left some standing water on the ground, which would have allowed more near surface cooling. And so that's why we're seeing this. So we're going to have to be very careful with looking at specifically when convection is and trying to make sure that we give a good berth between when something is going to disrupt the atmosphere and when we start to reassume that temperature changes are due to urban effects. So I don't know if specifically our calculation is going to change. It's more like we need a bunch of if, else, et cetera statements after the fact to do some screening on what specifically is an urban heat island intensity and what is an urban heat island intensity and something else.
Yeah, I guess my follow-up to that was one thing I think would be really interesting to see is looking at your sites and looking at the component of surface reflection from those sites.
Yeah.
So maybe, I don't know, calculating the BRDF or something along those lines, right?
Sure.
Of looking at the surface reflection. I mean, you kind of already did that with the 2 versus 10 meter temperature. I think that's probably part of the differences.
Sure.
But just looking at the actual, component of surface reflection could be helpful, I think.
Yeah, no, thank you for pointing that out. And that's actually something that some researchers have developed previously and also used with the joint urban campaign analysis with the Oklahoma City Micronet. It was a differentiation of surface land types. And I think there were something like 30 different classifications for everything from rural to, purely urban. And so you can get into classifications like that using like Landsat data and all that jazz. So this is definitely an area we can get into. So whether it's using specifically BRDF or something like that, or land surface temperatures, yeah, but that's definitely somewhere where we want to take this analysis.
Yeah, there's definitely value in looking at like satellite data and basically you would be deriving the surface urban heat island.
Right.
But like you started out at the beginning, that's not the same as the canopy or boundary layer urban heat island. And
right.
In many ways, we are more interested in getting a good understanding of what the air temperature differences and gradients look like. So yeah, I mean, I think what you're really trying to do is going beyond this particular equation, using more the whole data set, which provides spatial variability of temperature and see how that varies. The challenge is going to be getting the data.
Yes, most certainly.
So yeah. Because the TCEQ data, for now, we only have 1 week of data, correct?
Yes.
So, yeah. You have another question?
Yeah. Would it be fruitful, I guess, is a way of putting it, to see how quickly the background site recovers from convection versus the urban island or the urban site recovers from convection? So does it heat up faster in the urban, or is there some cooling that's getting trapped here that results in a slower warm up than what would be rural?
Sure. I could see that becoming something that is related to what we look into. Whether that's going to be one of the things we try to target specifically, I'm not certain. Just because, once again, Houston is so darn complicated that isolating that might be a whole project in and of itself. But I don't doubt that there's something there. I just don't know if it's going to be within the scope of this specific analysis.
Any other questions or comments from anybody? Ottavio?
Do you have an assessment of how much the urban area affects our layer? I expect it to be higher in the urban region than outside of it. And that would also affect temporal composition.
Most certainly.
That would be an indirect effect that you're looking at.
Yes, yeah, most certainly. So that's a great point. So I have not looked at boundary layer heights explicitly yet myself, but thankfully due to Tracer, we do have some measurements of that. Whether those boundary layer height measurements are going to be specifically at the sites that we're going to deem urban versus background, that's a little bit more up for debate. But at least we can get some context as to what the boundary layer height looked like during the evolution of the campaign. And that will certainly give us some more information to use and to analyze.
Have a guess or
Yeah, Michelle is actually, Michelle Spencer is working on that as part of her PhD. And we do have that analysis for the clamps data. And if you go back to your map, maybe we can quickly point out where the clamps are located. So
Yeah.
you see, well, maybe you can navigate to the coastal center really quick.
Yeah, it's around this region.
The mouse is not seeing.
Oh, I'm sorry. It is around this region. Approximately is where the coastal center was. And then there was another site. Was it in Sugarland or was it Seasepper was over here?
Right in that area.
Yeah. And then we had another one, Aldine, which is right around here.
So we don't have a measurement inside the downtown area, so not
Right.
exactly where all those red dots are clustering that listeners used to as an urban area to focus on. But we clearly see that the boundary layer at the site downwind of the urban area, north of the urban area, the boundary layer is steeper.
Yep.
And
by how much?
I don't know off the top of my head. I don't know if Michelle is online. Is she online?
Sure.
She is.
Did she hear the question?
Yeah, I haven't been.
No, I couldn't hear the question itself. The maximum distance is a difference between clamps 1 and clamps 2, which are the most different two out of the sites, is on average about a half a kilometer, but it varies at the different time of day. So you do see a few hundred meters different in the heights during the overnight period, and also a difference in heights during the day between the two different sites. And you do see a difference also with days with sea breezes versus no sea breezes.
So that's kind of the long-term goal is to connect the analysis that Elizabeth is doing with the boundary layer observations. And really, because right now we don't know what the urban heat island intensity was like, or what the temperatures over the Houston urban area were like when we have those measurements from the clamps. And that's the piece of information that we want to use to better understand what we see in the boundary layer. So we need to connect those two pieces. Any other questions, comments for Elizabeth? Yes.
So I have a question. So could the urban island change like the frequency of cloud cover or things like that? Or convection, that other things?
That's a good question. I've seen arguments before that the urban heat island might have an influence on convection. I don't have a specific a theory at this point with Houston specifically, simply because that's the statement I always go back to when dealing with Houston data. It's darn complicated. From my observations on the ground being there during the campaign, I question if it would have a major influence. But I'm not saying that there's no connection. So.
There are actually a lot of papers, mostly based on numerical studies, that say that the urban areas have a strong influence on convection and precipitation patterns, that storms are splitting around cities. But a lot of the traditional convection scientists, even coming from this building, have always been somewhat skeptical of those conclusions, because storms are splitting often when there's no city around. So that's one of the challenges. Yes, there are a lot of simulations that show that if you include some so-called urban canopy parameterizations in the models, you see differences, and that the storm trajectories change, that the precipitation intensity changes, that the location of where precipitation happens near cities is different if you run models with and without the city, but whether there's still skepticism about those results. Let's just put it at that.
Yeah.
So, because it's primarily model based.
So.
Okay, then let's thank our speaker one more time, and